Welcome to the Deep Dive. Today we're diving into some really big questions, the kind that, well, keep astronomers up at night. Questions like, how did these incredible structures, galaxies, actually form? How did they evolve over billions of years? And maybe even more fundamentally, where did all the stuff needed for life, carbon, oxygen, iron, where did that actually come from? How did it get spread across the universe? These are huge cosmic puzzles, and they tie directly back to, well, us. Our own origins.
Absolutely. And, understanding these isn't just about curiosity. It's about tracing our cosmic history, understanding the physics that governs everything. But the real challenge, as you hinted, is time. We can't just sit and watch a galaxy form. It takes billions of years. So astrophysicists have to get creative. They build these incredibly detailed numerical simulations, basically, virtual universes in a computer.
Right, building virtual universes. And that leads us straight into today's deep dive. We're going to zero in on something pretty groundbreaking, a development that's really speeding up how we tackle those big questions. We're talking about how cutting-edge AI, artificial intelligence, is being used in a really clever way. It's helping simulate how galaxies evolve, specifically focusing on those really powerful, dramatic events, supernova explosions.
Yeah, it's fascinating stuff. Our discussion today is grounded in some brand new research led by Keiya Hirashima and a team from RIKEN, the Max Planck Institute for Astrophysics, and the Flatiron Institute. Their work just got published in the Astrophysical Journal, and it really represents a significant leap in how we can model the cosmos computationally.
Okay, so our mission today is to unpack exactly how this AI approach works. How efficient is it? And maybe most importantly, what does it really tell us about the universe, about how stars form, how galaxies live and die, and ultimately about where we came from? We'll get into the nitty-gritty of the AI training, how it meshes with traditional methods, and what the first results look like. So let's start with the big picture, the cosmic challenge. Simulating galaxies. You said we can't watch galaxies form in real time. So these simulations, just how massive an undertaking are we talking about? What goes into building a virtual galaxy?
Well, yeah, it's a central problem in astrophysics. Since direct observation over billions of years is out, simulations are really our only window. Think of them as digital labs. You test theories, you tweak the physics, you watch processes unfold that are otherwise totally invisible. It's essential.
And I imagine it's more than just pretty pictures. What kind of data, what kind of physics goes into making these simulations, well, realistic?
Oh, much more. They're built on mountains of observational data from telescopes across the spectrum, radio waves, X-rays, you name it, measuring everything we can about interstellar space. But the real heavy lifting is the physics. You've got gravity, of course, orchestrating the big cosmic dance. Then there's hydrodynamics, that the movement of all that gas and dust, how it flows, collides, heats up, cools down. It's like galactic weather, but way more complex. And on top of that, you need astrophysical thermochemistry, how heat and chemical reactions change the gas. Does it cool and form stars? Does it get blasted away by explosions? All these pieces interact in really complicated feedback loops. It's computationally very demanding.
Wow, okay. Gravity, gas flows, chemistry, heat.
Yeah.
That's a lot to track. The computing power must be immense. But you mentioned a specific bottleneck earlier, something about temporal resolution. What exactly is that, and why is it such a headache for these simulations?
Ah, yes, the temporal resolution. That's where things get really tricky. To capture critical, fast events, and supernovae are the prime example. Incredibly energetic and brief, your simulation needs tiny time steps. Think of it like taking snapshots. If the time between your snapshots is too long, you completely miss the crucial rapid action. You basically blur out the important physics. And this leads to a really nasty problem called numerical overcooling.
Overcooling. That sounds wrong for a supernova. What does that mean in practice?
Yeah, it sounds weird, but it's a huge simulation nightmare. Imagine the super hot gas from a supernova, which should be expanding violently, pushing everything outwards. In a simulation with time steps that are too large or resolution that's too coarse, that hot gas cools down way too fast, artificially fast. It's like pouring water on a hot pan and having it instantly freeze instead of boiling away. So the simulated supernova fizzles out too quickly. It doesn't push the gas around realistically. It doesn't create the structures we see. It messes up star formation rates. It's been a major roadblock.
Okay, so to avoid that, to capture something like a supernova properly, how small do these time steps need to be? What kind of time scale are we talking about?
We're talking incredibly small. To capture that initial blast phase of a supernova shell expanding into the surrounding gas, you need time steps of just a few hundreds of years. Now remember, these simulations cover billions of years, so hundreds of years per step is tiny. It's roughly 1,000 times smaller than the time steps you might use for the general large-scale evolution of the galaxy, which could be millions of years. It's like trying to film a hummingbird's wings with a slow-motion camera designed for glaciers.
Hundreds of years per step for billions of years of simulation. That sounds computationally crippling.
It absolutely is. The cost is enormous. Let me give you a sense of this time step bottleneck. Even with a powerful supercomputer running a simulation of just a relatively small dwarf galaxy, if you need that fine temporal resolution for supernovae, it can take 1 to 2 years. 1 to 2 years of continuous supercomputer time for one single simulation. That's a massive investment of resources and time. It severely limits what scientists can explore.
Okay, so that's the mountain they needed to climb, which brings us back to the AI. This is the cosmic shortcut you mentioned.
Precisely. This is where Keiya Hirashima and the team came in with their really innovative approach. They specifically targeted this time step bottleneck and the related overcooling problem by bringing AI into the mix. The goal was basically to keep the accuracy high but drastically cut down the computational time. Work smarter, essentially.
And their solution is this framework, Asura FDPS ML. Quite a name. The ML for machine learning is key. What's the core idea? What is surrogate modeling?
Right. Asura FDPS ML is a clever hybrid. It combines the traditional detailed physics calculations with what's called surrogate modeling using machine learning. Think of a surrogate model as a highly trained stand-in or maybe a stunt double. Instead of doing the incredibly complex step-by-step calculation for something like a supernova explosion every single time it happens, which takes ages, the AI learns to predict the outcome. It's trained to know what the gas should look like after the explosion based on what it looked like before. It becomes a super fast, accurate proxy for that specific, difficult piece of physics.
Interesting. So the AI isn't simulating the entire galaxy. That'd be too much, right? It focuses on the tricky parts, the supernovae.
Exactly. That's the smart part. Teaching an AI to simulate a whole galaxy from scratch, still way too hard. Instead, they trained it on a very specific, high-detail dataset. They fed it 300 separate, high-resolution simulations of just a single supernova exploding inside a dense molecular cloud, a cloud with about 1 million times the mass of our sun. So the AI became an expert on just one thing, the immediate aftermath of a supernova.
And what kind of AI are we talking about? Is it a specific type good for this kind of 3D dynamic data?
Yeah, they use a specific type of neural network called a UNet. It's an architecture often used in computer vision, like for medical image analysis, because it's really good at understanding spatial structures, seeing both the fine details and the bigger picture. In this case, it learns the 3D gas dynamics, density, temperature, velocity around a supernova, how the energy spreads, how the shock wave moves, and the training data was incredibly fine-grained, down to a resolution of just 1 solar mass per particle. That let the UNet learn the physics really accurately.
So after learning from those 300 supernova examples, what can the AI actually predict? What does it output?
Okay, so after all that training, it got really good at predicting the state of the gas density, temperature, and the 3D velocities about 100,000 years after a supernova goes off. You feed it the 3D state of the gas before the supernova, represented as a grid of 64 by 64 by 64 voxels, like 3D pixels, and it predicts what those fields will look like 0.1 million years later. It essentially learns the effect of the supernova over that specific time window without needing to calculate every tiny step within that window. It's a clever shortcut.
That is clever. So you've got this specialized supernova predictor. How do they weave that into the main galaxy-wide simulation? What's this hybrid calculation strategy?
This is where the elegance of the Asura FDPS ML system really comes through. The main galaxy simulation runs on the bulk of the supercomputer's processors, the main processes. These track gravity, overall gas movement, star formation, using a fixed, longer time step, 2,000 years in this case. That's efficient for most of the galaxy's slow evolution.
But 2,000 years is way too long for a supernova, as we established. So when a star explodes in the simulation, what happens? Does everything just stop?
Exactly. That's the trigger point. When a supernova occurs, specifically in a dense region, they defined that as more than 1 hydrogen atom per cubic centimeter. The main simulation pauses for that localized event. They focus on dense regions because that's where the traditional method really struggles with that overcooling problem we talked about.
Okay, main simulation pauses. The supernova event is isolated. Then the AI steps in.
Precisely. The gas particles in that dense region around the supernova get sort of temporarily handed off to separate pool processes. Think of these as dedicated AI specialists. In these pool processes, the trained AI surrogate model takes over. Instead of the slow, direct calculation, the AI quickly predicts what those gas particles should look like 0.1 million years later after the supernova's initial blast. That 0.1 million year window is key long enough to cover the really fast problematic phase, but short enough that the larger galaxy structure hasn't changed much.
And once the AI makes its quick prediction, how does that get folded back into the main simulation?
Well, conceptually simple. Once the AI has its prediction, and the main simulation clock has also advanced by that same 0.1 million years, the updated gas particles with their new AI-predicted density, temperature, velocities are sent back from the pool to the main processes. The main simulation then just picks up where it left off, seamlessly incorporating the effect of the supernova, but having saved a huge amount of computational time. It's also worth noting supernovae in less dense regions where the overcooling isn't such an issue are still handled by the old direct calculation method. So it's a targeted approach. The AI only steps in where it's most needed and most effective.
That's a really smart division of labor, like having a specialist consultant for the hardest parts. So the big question, what's the speed up? How much faster is this AI-assisted method?
The results are pretty astounding. Keiya Hirashima, the lead author, put plainly, when we use our AI model, the simulation is about 4 times faster than a standard numerical simulation. Think about that. What used to take 1 to 2 years on a supercomputer can now potentially be done in, say, 3 to 6 months. That's a reduction of several months, maybe half a year, of computation time per run. That's huge in this field.
4 times faster. That is a massive leap. It opens up so many possibilities for running more tests, exploring more parameters. But the crucial question always is accuracy. Did they sacrifice accuracy for speed?
That's always the worry, isn't it? But this is where the story gets even better. According to their paper, this speed-up did not compromise accuracy. They state the AI-assisted simulation was able to reproduce the dynamics important for capturing galaxy evolution and matter cycles, including star formation and galaxy outflows. So the core physics driving how galaxies live and breathe is still captured correctly. They even optimize the AI prediction part itself so it doesn't become the new bottleneck. It's fast and accurate.
Okay, fast and accurate is the claim. But they had to prove it, right? How did they actually test this? What was their virtual cosmic laboratory?
Right, they needed a rigorous test. So they applied it to simulating an isolated dwarf galaxy. Think of it as a controlled experiment. It wasn't just a random galaxy model. It was based on known characteristics. A virial mass of about 20 billion solar masses, much smaller than the Milky Way, but a good testbed. It had specific initial amounts of gas and stars.
And the detail. How fine-grained was this test simulation?
Very detailed. They used 4 million dark matter particles, 10 million gas particles, and 5 million star particles. The resolution for normal matter, the gas and stars, was down to just 4 solar masses per particle. That's incredibly fine, allowing them to resolve small structures, individual star-forming clumps. The texture of the gas is like zooming way in.
You also mentioned it was pre-volve. What does that involve for a simulated galaxy?
Yeah, that's important. Before starting the main comparison runs, they let the simulated galaxy evolve on its own for 500 million years using older code. This lets it settle down, develop realistic turbulence and density variations, just like a real galaxy would over time. It prevents artificial effects, like a sudden unrealistic burst of star formation right at the beginning. Just because the initial setup was too smooth or uniform, it gives it a more natural starting point.
Okay, so they set up this realistic dwarf galaxy. Then they ran 2 versions. The traditional direct method called SNDT, and the new AI-assisted one, SNML. How do they compare visually? Did the galaxies look the same?
Visually, looking at the gas density from above, the morphology, they reported little difference. Both simulations clearly showed the formation of superbubbles, those big empty regions carved out by multiple supernovae going off near each other. And that's a really key validation point. Getting superbubbles right usually requires that very fine time resolution to avoid the numerical overcooling problem. The fact that the AI method, SNML, reproduced them correctly, even though its underlying time step was longer, shows it's effectively capturing that crucial feedback physics. The pictures look remarkably similar.
Impressive visual agreement. What about the engine of the galaxy star formation? Did the AI model match the traditional one in terms of how many stars formed over time?
Yes, the star formation rates over the simulation time showed very similar trends. There were tiny differences here and there. The traditional model had slightly more stars forming early on, the AI model slightly more later. But the total amount of stars formed, the integrated history, agreed within just a few %. That's well within the expected noise or variation you see even running the same complex simulation twice. So basically, excellent agreement on star formation.
Okay, looks all right. Form stars at the right rate. What about the internal structure of the gas itself? The different phases, cold, warm, hot gas. Did the AI capture that complex mix correctly?
This is another area where the agreement was remarkably good. They looked at what are called phase diagrams, plots, showing how much gas there is at different densities and temperatures. Both simulations clearly showed the expected three-phase structure driven by supernovae, a very hot, low-density phase, a stable, warm, medium-density phase, and a stable, cold, high-density phase where stars form. The AI model had a tiny bit more gas in a sort of unstable transitional state, but the actual mass difference was negligible. So yes, it seems to capture the complex thermodynamics of the interstellar gas extremely well.
All right, so the AI simulation seems to be nailing the basics. Looks, star formation, internal gas structure. Faster and accurate, but supernovae do more than just make bubbles. They drive these huge galactic outflows, right?
Right.
Let's talk about the outflows of creation. How critical are these winds?
Oh, they're absolutely critical. Supernovae are the engines driving these galactic outflows, or winds. These outflows are essential for regulating star formation. They blow gas out, stopping the galaxy from forming stars too quickly and running out of fuel. And crucially, they're how heavy elements, carbon, oxygen, iron, forged inside stars get spread out from the galaxy into the surrounding intergalactic medium. This enriches the cosmos, eventually allowing planets like Earth and life to form.
Wow.
Understanding outflows is fundamental to understanding our chemical origins.
So how do you measure these outflows in a simulation? Is it just how much stuff gets blown out? And did the AI get this right too?
They measure both the mass leaving the galaxy per unit time, mass outflow rate, and the energy carried by that outflowing gas, energy outflow rate. They also calculate loading factors, which compare these rates to how fast the galaxy is forming stars or having supernovae. It tells you how efficient the feedback is. And a really key finding, which the AI model reproduced very well, is that mass and energy travel differently in these outflows. It's not just one uniform wind.
Different transport for mass and energy. How does that work?
Well, if you look relatively close to the galaxy disk, maybe about 1 kiloparsec up, that's about 3,260 light years, the outflow is a real mix. You've got some cool gas that's moving slowly, maybe rising and falling back like a fountain. You've got cool gas that's been caught up and accelerated by the hot wind, and then you have the really fast hot wind itself. Now, the cool parts, especially that fountain gas, actually carry most of the mass leaving the galaxy's vicinity. But the hot wind, even though it might be less massive overall, carries most of the energy. That distinction is vital.
Okay, so a complex mix close in with cool gas carrying mass and hot gas carrying energy. What happens further out, say 10 kiloparsecs away? Does it simplify?
Yeah, it changes quite a bit to go higher. At 10 kiloparsecs, which is pretty far out, maybe a third of the way across the Milky Way's diameter, things have evolved. That cool, slow fountain gas has mostly dropped out or dissipated. The cool, fast gas gets mixed into the hot wind. And the hot wind itself cools down as it expands what's called adiabatic expansion, and also by mixing with the cooler stuff. This explains a critical observation. The total mass outflow rate drops significantly by about a factor of 10, between 1 kpc and 10 kpc, but the energy outflow rate only drops by about a factor of 2. The AI simulation captured this difference in how mass and energy flow at different distances really well, matching the traditional model.
That's a subtle but really important point for understanding how galaxies pollute their surroundings. The AI seems to be handling these large-scale effects too. What about the speed? Does the wind get faster as it goes out? Is there a sound barrier involved?
Good question. Speed is definitely part of the picture. Close in, at 1 kiloparsec, the hot wind is often transonic or mildly supersonic, moving around, or just above the local speed of sound in that gas. But as it travels outwards and expands into lower density regions, it accelerates dramatically. By 10 kiloparsecs, the hot wind becomes strongly supersonic, reaching Mach number speed relative to sound speed as high as 30. Both the traditional and the AI models showed this transition from roughly sonic speeds near the disk to highly supersonic speeds far out, which agrees with other studies too.
Wow, Mach 30. That's serious speed. Again, impressive agreement. Were there any small differences in the outflows between the AI and traditional models?
There was one minor point. At the highest altitude, 10 kiloparsecs, the AI model's hot outflows showed a few more particles trailing at lower speeds compared to the traditional model. This suggested the AI outflows might carry slightly less overall momentum, maybe about half as much. But the researchers think this might just be a sampling effect. There are very few gas particles way out there, so the statistics get noisy. It's probably not a fundamental flaw in the AI, just a consequence of having less data to work with at those extreme distances.
Okay, so Overall, the AI simulation seems incredibly robust, fast, accurate on morphology, star formation, gas structure, and even these complex large-scale outflows. This brings us to the really exciting part. Beyond the simulation, implications and future horizons. What are the big takeaways here?
Well, one of the most intriguing findings actually relates back to where the supernovae go off. In the traditional simulation, SNDT, they saw two main environments for explosions: very dense gas clouds where stars form, and very diffuse gas inside old superbubbles, a sort of two-hump distribution.
And the AI model, did it show the same pattern?
Interestingly, no. In the AI-assisted simulation, SNML, the peak of explosions happening in dense regions shifted to lower densities, significantly lower by about a factor of 3. So overall, the supernovae in the AI model tended to explode in somewhat more diffuse environments compared to the traditional run.
Huh. Why would that happen, and why does it matter where they explode?
This is really interesting. It suggests that the supernova feedback is actually more effective in the AI model, particularly in those dense regions. Remember the overcooling problem. The AI, by using its knowledge learned from higher resolution training simulations, seems to allow the hot bubbles to expand more efficiently, even within the lower resolution galaxy simulation. This means they clear out their surroundings better. So the next supernova in that area is more likely to explode into an already partially evacuated lower density region. This makes the overall feedback process more powerful, more realistic perhaps. And the data backs this up. The AI run actually had more supernovae overall, about 20% of massive stars exploded, compared to the traditional run, about 13%, suggesting the feedback wasn't being artificially suppressed as much.
So the AI isn't just faster, it might actually be doing a better job of capturing the physics by overcoming that old numerical limitation. That's huge.
It certainly looks that way, yes. It's a really promising sign.
So, stepping back, what does this fourfold speedup really mean for the field of astrophysics? What doors does it open?
It's genuinely a game changer. That speed up means simulations that took years can now be done in months. This lets researchers run many more simulations, test more variations, explore higher resolutions, tackle more complex physics. It accelerates the pace of discovery dramatically. Instead of one PhD student getting one simulation run done, maybe they can do 4 or explore a much wider parameter space. It's transformative.
And are they already using this power for bigger projects? What's next on the simulation list?
They absolutely are. The team explicitly states the new framework is now being used to run Milky Way-sized galaxy simulations. Simulating something as massive and complex as our own galaxy at high resolution has been incredibly challenging, borderline impossible before. This new AI-powered approach promises unprecedented detail in understanding our own galactic home, how the elements were distributed, how the structures we see formed. It's really exciting.
Simulating the Milky Way like never before. That's incredible. Where else could this cosmic AI approach lead? What other problems could it tackle?
Oh, the potential is enormous. The immediate goal is enabling these detailed, almost star-by-star simulations for even heavier galaxies, maybe up to Milky Way mass or even larger, down to resolutions of just a few solar masses. That's resolving individual star clusters. But beyond that,
Could it be used for other processes besides supernovae? Other types of feedback?
exactly. The researchers suggest developing similar AI surrogate models for other complex, computationally expensive stellar feedback processes. Things like photoionization, the radiation from hot young stars carving out HII regions, or the heating effect of ultraviolet light. If AI can accelerate those calculations too, it could allow us to study things like triggered star formation, how one generation of stars sets off the next in much greater detail across entire galaxies.
And what about the very, very beginning of a supernova, that first instant? Is that still too fast even for this AI?
That's another frontier. This study focused on the phase after the initial blast, the CDOV phase. But the potential is there to apply machine learning to model those very first free expansion moments too. Those require even shorter time steps and even higher resolution. If AI can help bridge that gap as well, we'd have a near-complete, highly efficient model of supernova feedback from the first fraction of a second out to its galactic-scale impact millions of years later.
What an incredible journey. We've really seen how blending AI with traditional simulation isn't just about speed. It's potentially about deeper accuracy and tackling problems that were just out of reach before. From the tiny details of an explosion to the grand sweep of galactic evolution, AI is becoming a vital tool for understanding the cosmos.
It really is. It empowers scientists, removes old barriers, and lets us ask more fundamental questions about how everything, including us, came to be.
Exactly. And thinking about that, this deep integration of AI and astrophysics, It feels like more than just faster computers. It's pushing the boundary of what we can even simulate, what we can know about the past. It makes you wonder what new aha moments are waiting just around the corner now that we can run these incredibly detailed simulations. What will they reveal about star birth, galaxy life, and maybe the precise pathway that created the elements essential for you and me? We're definitely entering a new era of cosmic exploration, powered by both human insight and artificial intelligence.